Good morning. I am, as said, Michele Modestino from University of Salerno, a PhD student under the supervision of Professor Massimiliano Polichetti, and I'm here to talk about, sorry, I lost my presentation in my screen. Okay, and I'm here to talk about magneto-optical, our magneto-optical study on iron oxide magnetic nanoparticles embedded in a keratin thin film. First of all, I want to show this purpose of our work because in a lot of applications of magnetic nanoparticles are used in matrices or generally in organic matrices for biomedical application. It could be important to study not only the bulk magnetic properties, but also magnetic properties in the scale of micrometer. So, with the help of our collaborator, we start from a mixture of nanoparticles and keratin to obtain a combined mixture. And starting from a droplet of this mixture, after spin coated it, we obtained thin films of thickness of around 200 nanometers, one with only keratin and the second with the presence of magnetic nanoparticles. Starting from the EFM images, and in particular by increasing magnification, it is possible to observe that the surface of these two samples are quite different. In fact, the surface of keratin thin film is practically flat, with only strange structure of thickness near 20 nanometers. And these are crystallization of keratin that completely disappear with the introductions of magnetic nanoparticles. And this structure was substituted by the presence of highest structure with 200 nanometer of thickness. This situation can be also observed by SEM image. In fact, it is possible to observe again the presence of this highest structure in a flattened area. And after the analysis of these different regions by EDX spectrum, it is possible to see that in the highest area, there is the presence of iron atoms that completely disappeared in the case of flattened regions. So, starting from these characterizations, we are able to see that nanoparticles are agglomerated in these regions with the highest thickness. And in our magneto-optical study, this was important information to search magnetic nanoparticles. More details about these preliminary characterizations are present in the reference. And before to start with magnetic optical characterization, we performed a magnetic characterization on the bulk material using a physical property measurement system by quantum design, equipped with a superconducting magnet with the maximum field of 19,000 Hz, with an ever-cool second option that gives us the possibility to work in temperature. And we used a vibrating sample magnetometer to perform a DC characterization. In particular, we studied the magnetization of SS field at 5 Kelvin and at 300 Kelvin of this sample. And it's possible to show that the coercivity field is reduced with the increasing of temperature, and in particular, it's quite near to zero. And this, combined to the fact that the shape of the magnetic loop is practically the same at low temperature and highest temperature, give us the information that this sample shows a superparamagnetic behavior with a strong response to magnetic field, but less coercivity. This was an important information for magneto-optical characterization because in this case, we know how to search magnetic nanoparticles and what type of magnetic behavior to expect. We used the Nanomaterials by Durham Magneto-Optics to perform our MOC characterization. We used the polar configuration in our case, and the AC field, for the AC field, we used it to perform the loops. We used a maximum amplitude of 200 Hz in our case at a different frequency. And we used also a cryostation by Montana Instruments to work also in temperature. I want to start by showing you the reflectivity images obtained by Nanomaterials for the sample of keratin and the sample with magnetic nanoparticles. As can be seen, as in this case, it is possible to observe for keratin flattened regions, but with the adding of nanoparticles, this flatness disappears, and there is the introduction of these regions that are the agglomerate of nanoparticles. In this case, they appear as black because the light is deflected by these regions. Okay, first we started by comparing the reflectivity maps with the maps obtained by considering the Kerr signal at 200 Hz. To obtain these maps, we performed a loop with AC fields for each pixel of the maps with a distance between pixels of 5 micrometers. And by considering the maximum signal for each micrometer, the Kerr signal to 200 Hz, we obtained these maps. As can be seen in the case of keratin, the signal is practically the same and is quite near to zero, but with the introductions of nanoparticles, the Kerr signal is increased, and in particular, if we compare this image with the one of reflectivity, it is possible to observe that the highest signal is associated to the region with the biggest agglomeration of nanoparticles. Okay, after knowing this information, we used this to evaluate the Kerr signal loops obtained for these regions, and in particular, we concentrate on the region with biggest agglomeration by performing an average of all the loops in this green square, and by comparing to the average of all the loops on the keratin surface, and these are the results at different frequency. As can be seen, in the case of nanoparticles, the loops are quite similar to the one expected for magnetic nanoparticles, but with the increasing of frequency, they have a distortion, and this distortion is also present in the case of keratin loop. So, by considering the keratin as a background for our samples, because nanoparticles are embedded in keratin, we performed the subtraction of the signal of keratin, and after this, we obtained the Kerr signal versus fields associated only to magnetic nanoparticles. These loops are quite similar to the one observed in via PPMS, and we obtained this loop at different frequency. But next step was to compare the loops obtained by averaging in different regions on the sample of keratin with nanoparticles, and we see that in all the regions, there is the presence of a signal that could be associated to magnetic nanoparticles, but with the lowering of agglomerate of nanoparticles in the regions, also the signal is lowered, as we expected. But our next and the last step was to introduce the temperature as a parameter. In fact, we performed the loops only on the green square at lowest frequency, the frequency of 0.5 Hz, just to compare this measurement to the one obtained by DC characterization. And we performed the loops at 300 kelvins and at 14 kelvins. The loops obtained at 14 kelvins is obtained after the subtraction of the keratin signal at 14 Kelvin. And as can be seen, the coercivity field is reduced, but if we compare the coercivity field obtained by Nano-Mach3 and the coercivity field obtained by PPMS characterization, it is possible to see that the coercivity fields are different, but it is due to the fact that in case of PPMS characterization, we used a sweep rate for the field of 0.5 Hz per second, but in the case of Nano-Mach3, also at the frequency of 0.5 Hz, the sweep rate is of around 200 Hz per second. So this difference in sweep rate justifies the difference of coercivity field evaluated. In conclusion, we demonstrated the possibility to characterize magnetic nanoparticles in organic matrices. In particular, in our case, magnetic nanoparticles are randomly distributed, and this is very important because generally, when magnetic nanoparticles are characterized by Mach, they are deposited on the surface, but in this case, they are only spin-coated. It is also possible to distinguish from signal in different regions and compare it. And it was also possible to observe a superparamagnetic behavior by comparing measurements performed at different temperatures. Obviously, this is only a preliminary study, And next step was to introduce different concentrations of nanoparticles, characterize more regions of nanoparticles, and to compare more temperature to obtain a study of the change of coercivity in temperature. I want to thank my laboratory and my collaborator for this work. I want to thank the organizer of this conference to give me the possibility to talk about it. And I want to thank all of you for your kind attention. Thank you so much.
Thank you, Michele, for this great presentation. So, do you have any questions for Michele? So I just have, okay, let's go, yeah.
Yeah, I have a very small question. So what what's the outlook of your observation? What's the next in case of like optical switching, all kind of this stuff? What is the next step in out of your study?
Please, can you repeat what is?
It's like magneto-optical research. So how your research finding will contribute to all optical switching devices?
We didn't think about the possibility to proceed in the optical devices. We think about the possibility to perform characterization for biomedical applications. In particular, the use of keratin with magnetic materials is thinked to application in bone remediation. So our study was more concentrated on the possibility to characterize the distribution of magnetic signal, because in biomedical applications, you don't have a lot of materials introduced in the body. It could be important to understand if nanoparticles are agglomerated and the signal is lost in some regions, or if your nanoparticles are distributed equally on the matrix, and also the magnetic signal is distributed in this way. So in case of optical devices, I don't have any idea. But in case of biomedical application, this could be interesting to study the best combination of matrices and concentration of nanoparticles to obtain the best distribution of magnetic signal. This was our purpose.
Yeah, that's very interesting. Thank you, Michele, again for your presentation.